In this video, we're going to take a look at the idea of power series. So basically, what we're going to do is we're going to have an infinite polynomial. So think of writing a function which itself is just an infinite polynomial. So something like f, g, or h on this picture. Here, f has coefficient on the constant term of 1, coefficient on the x to the first term of 1, and then 1 over 2 factorial is the coefficient of x squared, and so on and so forth as we go down. G of x, obviously, coefficients are 0, 1, 2, 3 on each of the x to the nth power. So we just get infinite polynomials. Now, oftentimes we write polynomials this way, where it's just x to the first, x squared, x to the third, x to the fourth, so on and so forth. But we can also write a polynomial where we're taking x minus 2 to the first, and x minus 2 squared, and x minus 2 to the third, and x minus 2 to the fourth, and so on and so forth. So this idea of an infinite polynomial is really the idea of a power series. If x is a variable, then the infinite series of the form infinite sum a sub n times x to the nth power from n equals 0 to infinity is a power series. If I write the power series like this, then we say that this power series is centered at 0. We can center the power series at another value if we want by redoing the power series and centering it at some value like c. So we would take the infinite sum an, and then instead of having just x to the n, we can have x minus c to the nth power, summed up from n equals 0 to infinity. This is a power series centered at c. Obviously, when c is 0, then we just get our traditional x to the nth power. And then these coefficients can be anything that we want. So sometimes they could all be 1, sometimes they could be 1 over n factorial, sometimes they could be just n themselves. These coefficients are going to be some sort of, are going to form, or going to be a sequence, terms of a sequence. The big question we're going to ask in this section is, for what values, when I plug in, do I plug in for x? Does the power series converge? And for what values, when I plug in those values in for x, does the power series diverge? We often say, what are the values where the power series converges? Or just when does the power series converge? When does the power series converge implies what values does the power series converge for? Obviously, this is going to depend on what coefficients we have. So different power series are going to converge at different values of x. Some power series are going to converge at lots of values for x. Some power series are going to converge at almost no values for x. I say almost no value for x. It turns out for each power series, we're going to have 3 options. Let's have a power series be centered at c. then one of the following things has got to happen. Option one is that the power series only converges when x is equal to c. Now, think about what that means here. If I plug in a c for x, c minus c becomes 0. So therefore, we just summing up a bunch of zeros. So it always has to converge at least when you plug in c, because you get all zeros when you plug in c. And we're saying it does not converge for any other x values. So this is like the only place it converges is at c, and it diverges everywhere else. The second option is that the power series converges no matter what value of x you put in. So if I put in x of 5 or negative 18 or 136 or 5,800,000, the series will converge. So the series converges for all x is the second option. And basically that second option means this part is going to be a more important growth than this part. The x minus c of the n is going to be a less important type growth than the growth involving the a sub n's. And then the third option is the one that's probably the trickiest. The third option says there exists a real number such that the series converges absolutely when x minus c in absolute values is less than that real number, and the series diverges when the absolute value of x minus c is greater than that real number. Notice at the equal to the real number, sometimes it can converge, sometimes it can diverge. But basically what this means is the power series converges for certain intervals and it diverges outside of that interval, specifically an interval. So this third option is saying there's some interval out there where the series converges, and outside of that interval, the series diverges. We call that the interval of convergence. So those are the three options. Series only converges when you plug in C because you get all zeros. The series converges no matter what you plug in for X. And then the third option is there's an interval of convergence. Now, this goes back to the concept of faster orders of growth and slower orders of growth. So let me remind you of that. N to the n power is a faster order of growth than n factorial. So if we have a numerator, denominator that are doing one of each, the n to the n is going to be the faster order. That's going to determine what the fraction does. N to the factorial growth is faster growth than exponential growth. N to the p type growth is slower growth than exponential. Natural log growth is slower growth than n to the p, and then constant is like no growth. We're standing still. And what I am arguing is that the fastest order of growth is going to essentially dominate any series. Now, we do have to take into account multiple types of growth going on in the operation. So n to the n versus n to the n factorial, n to the n factorial, we have a lot of different growth going on. But essentially, the fastest order of growth is going to dominate in any series. So whatever that type of growth is, that determines whether the series converges or diverges. And the other slower types of growth are kind of like they're standing still by comparison. So if I can pick out the fastest, most dominant growth as n gets larger, as n goes to infinity, then I can simply focus on that one to determine the convergence of the series. Let's do an example. Let's say we want to find the interval of convergence or the radius of convergence for this infinite series. Infinite sum of n factorial times x to the n from n equals 0 to infinity. Now, what you'll see here is that we have two types of growth going on. We have an n factorial type growth and an x to the n type growth. Well, x to the n type growth, that is exponential. Or, I'm sorry, it's exponential. It's like b to the nth power. Now, obviously here, it's growth if b is greater than 1. It's decay if b is less than 1. But n factorial is a more dominant growth than b to the n, no matter what our b value is. And therefore, the n factorial is going to dominate because it has a faster order of growth. So in this infinite series, the n factorial dominates. Now, I'm using the language of dominates in a very loose way. Hopefully that's not too confusing. A lot of actual mathematicians might not use that language. All right. But I like that language because it shows me what to pay attention to. So the n factorial is the big, the big, the big kind of growth here. All right. So whatever I plug in for x, whether it's 15, whether it's 1/6, whether it's 22, the n factorial is going to eventually outgrow it. So this infinite sum is going to behave like this infinite sum for basically all values of x. Almost all, I should say. That's why I said basically. This obviously diverges. The infinite sum of just n factorial from 0 to infinity diverges. We know that. Therefore, this thing is going to diverge essentially for all values of x, except there is the one exception, and that's when I plug in 0. When I plug in 0, this is an infinite sum of all zeros. So I have to be careful about that. That diverges everywhere except when I plug in x of 0. So we say this infinite series only converges when x is equal to 0. So it only converges when we plug in 0. Let's take a look at example 2. It's an infinite sum of n factorial times x minus 2 to the n, summed up from 0 to infinity. So in my language, I would say n factorial dominates. It's the fastest order of growth around. Therefore, what it does is going to dictate. Again, I say n factorial dominates because x minus 2 to the n, once again, is exponential. So we have exponential versus n factorial. No matter what I plug in for x, this is exponential. So obviously this is the same sum other than where we're centered. And so I know the infinite summation of n factorial diverges. Therefore, the only hope of convergence is when we plug in an x of 2, because if I plug in x of 2, then I get all zeros. So this infinite power series only converges when x is, in this case, 2. Again, notice that both of those were very, very similar examples. One of them was centered, a power series centered at 0. Another was a power series centered at 2. These were different polynomials, but you could get certain same values by plugging in different values for x's. So in that case, so in this case, we have two types of growth, exponential and factorial. And the factorial growth dominated. Let's look at another example. Here we have n times quantity x plus 5 raised to the nth power. That all is in the numerator. The denominator is n factorial times 3 to the nth power. And that's all being summed up from n equals 0 to infinity. So let's think about the radius of convergence, the interval of convergence for this one. Now, this infinite series has multiple types of growth going on. Here, this is an n growth, n to the p type growth. X plus 5 to the n is exponential growth. 3 to the n is also exponential growth. And then n factorial is factorial type growth. Once again, we have n to the p, we have exponential, and we have factorial. The factorial growth is going to be the biggest type of growth, and therefore n factorial growth is going to dominate. Now, because of that, all of these other types of growth in the numerator and denominator are going to look like they stand still. In comparison, anyways. And we know that the infinite sum of 1 over n factorial from n equals 0 to infinity converges. We've seen that a couple of times. You can use a direct comparison test if you'd like. But infinite sum 1 over n factorial converges. And therefore, this infinite series is going to converge no matter, or this as an infinite series will converge no matter what x value you plug in. So this infinite series converges everywhere. Now, the question asked for the radius of convergence. If it converges everywhere, then technically the radius of convergence is infinity because we can go infinitely to the right and infinitely to the left of where our power series is centered. So when it converges everywhere, the radius of convergence is infinity, and the interval of convergence is from negative infinity to infinity. I typically don't ask that. And by the way, in our previous example, if it converges only at a single point, we say the radius of convergence is 0. So the radius of convergence is 0 when it converges only at a single point. Interval of convergence would just include the single number of 2. And down here, radius of convergence is infinite. Interval of convergence would be from negative infinity to positive infinity. Now, in these first 3 examples, the existence of the n factorial made my exponential growth irrelevant because n factorial is a faster type of growth than exponential. Therefore, we were in one of these first 2 options. The series only converges at a specific value like x equals 2, or the series converges for all values of x. You can guess what's going to happen with this third option, where we get a real number radius of convergence that's non-zero. That's going to be the case where the exponential growth is the fastest growth around. So the first 2 cases where the series only converges when x equals 0, or excuse me, x equals the center, or the series converges for all x, those happen when we have faster growth than exponential around. Like in our cases, n factorial was always there. If exponential growth is the fastest, then we're in a different scenario. Let's take a look at example 4. We want to find the radius of convergence and the interval of convergence of this power series. In this case, x minus 6 raised to the nth power, that's exponential. By the way, notice our sum started at n equals 1 because you don't want to divide by 0 in this case. But x minus 6 to the nth power is the fastest growth around. So the exponential growth of x minus 6 raised to the nth power is the fastest, or most dominant. And this n to the first power, like the n to the p type growth, is less dominant than exponential growth. So that means my power series is going to behave kind of like what would happen if I didn't have this divide by n. If I didn't have this divide by n, I would just have x minus 6 to the nth power in the numerator summed up from 1 to infinity. And what that is a geometric series. That is the same thing as taking r raised to the nth power. And we know that that is going to converge when r is between -1 and 1. So this is going to converge when r is between -1 and 1. And that means it's going to converge. What's my r here? Well, my r is x minus 6. So when x minus 6 is between -1 and 1. Adding 6 to all three sides tells me that this series converges when x is between 5 and 7. So that is the interval of convergence. Now, the radius of convergence is 1, because if you start at the center of 6, then you move 1 in each direction. So the interval of convergence basically is what I just wrote down. So it is any x value between 5 and 7. You can use interval notation if you want. You can use, I typically just use this notation. The radius of convergence is 1. I'll write capital R equals 1 so that I'm consistent with what we had on our slide. Again, it's 1 because that's the radius. You start at the center of 6. You go 1 to the left, you get a 5. You go 1 to the right, you get a 7. So the radius of convergence is 1. Anything within 1 unit of 6 or less than 1 unit of 6 will converge. Now, here's the weird thing. We know it diverges when x is bigger than 7 and when x is under 5. But at the endpoints, different things could happen. Now, at the endpoints, I have to go all the way back up and remember what my original summation was. So at the endpoints, we have to check manually. Okay, in other words, because it diverges, the original series diverges when r is going to be greater than 7 and r is less than 5. Okay. But we do have to check the endpoints. So let's plug in an x of 5 and see what happens. And then we'll plug in an x of 7 and see what happens. If I plug in 5, I just plug in 5 for x, plug in 7 for x next. Then this infinite summation, 5 minus 6, becomes a -1 to the nth power. This converges because it is an alternating series and the terms are going down to 0. If you forgot how to do that, go back to the alternating series section, but I'll just write it. It converges because it's an alternating series. I'll write it like that, I guess. So at that endpoint, it converges. At the other endpoint, when I plug in a 7, I get a +1 to the n. +1 to the n is just 1 over n. This infinite series diverges. And you can see that because it's a p series with p of 1. So in this case, the endpoint of 5, when I plug that in, works, but the endpoint of 7 does not work. This is kind of how all of these go, where the exponential part is going to be dominant. We say, oh, the exponential part is dominant, so if we ignore all the other stuff, it looks very much like a geometric series. And we know that geometric series converge when r is between -1 and 1. So when my geometric base is between -1 and 1, it converges and it diverges elsewhere, except for possibly the endpoints. And then I have to check the endpoints manually. So x equals 5 leads to convergence. X equals 7 leads to divergence. Let's look at another example. Here we have example 5. We have an infinite sum of x minus 2 to the nth power divided by 3 to the nth power times n squared plus 8, where 3 to the nth power times n squared plus 8 is in the denominator, and x minus 2 raised to the nth power is in the numerator, and we're summing all those terms up from n equals 0 to infinity. If you want to try this on your own, push pause on the video and do that. Once again, the exponential part is going to dominate, but we kind of have two exponential parts in here. We have an x minus 2 raised to the n divided by 3 raised to the n. So the exponential dominates. Again, that's a term that I use. And when I look at that exponential part, it's actually a combination of two things. And I'm going to rewrite that as one single expression. So what I'm going to do is take x minus 2 to the n divided by 3 raised to the nth power. And I'm going to rewrite that as just x minus 2 over 3. That is the quantity x minus 2 divided by 3, all raised to the nth power. And so this infinite series is going to behave similar to the infinite series if I just had x minus 2, keep doing that, x minus 2 over 3 raised to the nth power summed up from 0 to infinity. This is like a geometric series now that I've written it this way. And in a geometric series, I know that as long as my r is between -1 and 1, we are going to converge. And now my r is the quantity x minus 2 divided by 3. So as long as x minus 2 over 3 is between -1 and 1, we're good to go. To solve this, you'd multiply both sides by 3. So we get -3 less than x minus 2 less than +3. And then I'd add 2 to both sides, or all three sides, I should say. I'd end up with -1 less than x less than 5. And that is my interval of convergence. So my interval of convergence is from x, or excuse me, is from -1 up to 5. By the way, again, the radius of convergence, since we're centered at 2, it's pretty clearly that we're centered at 2. If we go 3 in each direction, we end up at the -1 and the 5. So the radius of convergence is actually 3. Again, if I want to be consistent with the notation from a previous slide, I'll have r equals 3. Now, this is the most important part, is the interval of convergence, radius of convergence. The calculation of the interval of convergence is the most important. But we always need to figure out what happens with our endpoints. So what happens when I plug in a -1? Not to this infinite sum, but to my original infinite sum. So that's why I can't just say it diverges when I plug in 5 and diverges when it plugs in 1. That would be the case if it was this geometric piece. But I'm talking about my original infinite sum. My original infinite sum has interval of convergence between -1 and 5 with a radius of convergence of 3. And when I look at the endpoints, well, if I plug in, let's plug in -1. If I plug in -1, I get -3 raised to the nth power divided by 3 to the nth power times n squared plus 8. -3 to the nth power over 3 to the nth power. That is just the same as -1 to the nth power. And my 3 to the nth power is going to cancel out with this 3. I could factor this out, in other words, -3 to the nth power. So if I plug in -1, I get this infinite series. This is alternating, so, and the denominator is getting really, really big. So the whole fraction's going to 0. So this is going to converge again because it's an alternating series. And if I use the alternating series test, I can see that this converges. What's going to happen when I plug in a 5? When I plug in a 5, I get 5 minus 2 to the nth power. That's 3 to the nth power on top. And I'd have a 3 to the nth power on bottom. So I'd end up with 3 to the nth power divided by 3 to the nth power. Those will cancel each other out. And I'll just be left with 1 over n squared plus 8 summed up from 0 to infinity. In this case, this also converges because it's a p series with p of 2. So because it's a p series with p of 2, this converges. So both endpoints have my original power series converging. So in this case, both endpoints led to convergence. In the previous case, one endpoint led to convergence, the other one led to divergence. And then obviously you could have an example where both diverged as well. But in this example, the interval of convergence, again, when I say the interval of convergence, I'm saying for this infinite series, this power series. So this power series has an interval of convergence between -1 and 5. The radius of convergence is 3. The endpoints, one of them causes convergence, the other one also causes convergence. All right, here's another example. So go ahead and if you want, push pause and try example 6. Once you've done a number of these, they can go pretty quickly. In this case, the exponential is the fastest growth, so it is going to dominate. That means this summation is not the exact same, but it's going to converge on the same radius as x plus 8 raised to the nth power. Whoops. X plus 8 quantity raised to the nth power. It's going to converge on that same radius. And I know that one looks geometric with r equals x plus 8. I know that when it's geometric, that we converge between -1 and 1 when r is between -1 and 1. So in this case, we want our x plus 8 to be between -1 and 1. Subtracting 8 from all three sides gives me my interval of convergence. So if I subtract 8, I get that my x value has to be between -9 and -7. Now, the center of this polynomial was -8. So going from the center down to -9 or going from the center of -8 up to -7 says that my radius of convergence is 1. So my interval of convergence is x between -9 and -7. My radius of convergence is 1. You go 1 unit both ways from the center. And that's not for just this summation. That's for my original series. So my original series, go here. I think we got that part. So this series has interval of convergence between this power series has interval of convergence between -9 and -7, and radius of convergence is 1. Now I want to check the endpoints. I have to check each of these manually. So I will start by plugging in a -9. When I plug in a -9, I get -1 to the nth power, all divided by n to the third. That infinite series converges. Again, we're using the alternating series test. Terms are going to 0 and it's alternating. With the other endpoint, when I plug in a -7, I end up with infinite sum of 1 raised to the nth power over n to the third, which is the same thing as just 1 over n to the third. This is a p series, and the p is 3, so this also converges. So that means this power series has an interval of convergence between -9 and -7, radius of convergence of 1, and it converges at x equals -9. It converges at x equals -7. Converges at both places. Both endpoints, sorry. This is the information that in my class you'd be asked to give. You'd be asked to give the interval of convergence, maybe the radius of convergence, and then whether it converges at each of these 2 endpoints. Let's do another example. And we'll try to find the interval of convergence, the radius of convergence, and the endpoints if it matters. So interval of convergence, radius of convergence for infinite sum of 5n squared times x minus 4 raised to the nth power divided by 7 raised to the nth power. Try this on your own if you'd like. All right, so exponential growth is the dominant growth here. Okay, again, we have n to a power type growth. We have x minus 4 to the n and 7 to the nth power. The x minus 4 and the 7 to the nth power are both exponential, so I'm going to combine them into one summation. The way I do that, well, when I say combine them in the same summation, what I'm doing is saying the exponential growth is the dominant growth. So the interval of convergence is going to be determined by that type of growth. Since I have ah, since I have two exponential pieces, I combine them into one single term. And so I'm going to get an infinite sum of x minus 4 over 7 raised to the nth power. We know through geometric growth that the geometric convergence that this is going to converge anytime that x minus 4 over 7 is between -1 and 1. So we write that out. Multiply both sides by 7. And then add 4 to both sides. I say both, I mean all three sides, I should have said. All three sides. Same thing, when I multiply by 7, I'm multiplying by 7 on all three sides. That is my interval of convergence for my original series. So again, my original series, this series here has interval of convergence between -3 and 11. I'll write that down here. So when x is between -3 and 11, we know the series converges. We are centered at 4. Our power series is centered at 4. So the radius of convergence, well, that is 7. If I have an x of 4, then that's the center. It's 7 units to hit the 11, 7 units down to hit the -3. So this series is dominated by the exponential piece. If I just pretended that the series only had the exponential piece, we'd see the interval of convergence. Since it's dominated by the exponential piece, the same interval of convergence will happen here as here, except the endpoints may be different. So now let's go and check the endpoints. I'll check those right here. If I plug in a -3, I get infinite sum. We'd get -7 raised to the nth power over 7 raised to the nth power. Those are going to cancel out, and the 5n squared will stay put. So we'll get 5n squared times -1 raised to the nth power. This is alternating, but it is growing. The terms are growing. Therefore, since the limit of those terms is not 0, this diverges. So that diverges by the alternating series. test. So this diverges because of the alternating series test. If I plug in the other endpoint of 7, not 7, excuse me, 11, what you'll get is 7 raised to the nth power divided by 7 raised to the nth power. Those will cancel each other out, and you'll just be left with 5n squared. And that also diverges. That's the divergence test, or the divergence rule. The terms don't go to 0. So in this case, both endpoints diverge. So the series diverges when x is equal to -3, and also diverges when x is equal to 11. Again, this is the information that I would be looking for in problems. Where is the interval of convergence? And then what happens at the endpoints? And then obviously the radius of convergence is embedded inside the interval of convergence. So there we go. Obviously, this is the first case when both endpoints caused divergence. In our previous example, we saw that both endpoints had convergence. And that was in our first example, one of our first examples, we had convergence at one endpoint, divergence at another endpoint. So you can see that any combination of endpoint convergence or divergence is possible. We can have one converge, one diverge. We can have both converge. We can have both endpoints diverge, just like we did in this last example. Now, don't forget that the other two options also exist. In the examples we have been doing, example 4, 5, 6, and 7, those examples were all cases where there was a real number, a radius of convergence greater than 0, so that the series converged on a certain interval and diverged outside of that certain interval. But if exponential growth is not the fastest growth around, then we're in the first two cases. The series only converges when x equals c. That's a radius of convergence of 0. Or the series converges for all x. That's a radius of convergence of infinity. And in those cases, we generally don't think of our interval of convergence as having endpoints, because one of them is infinitely long and the other is size 0. So it's trivial. So those two cases, don't forget about either. The only converges when we plug in x equals c, because then we get all zeros added up, or the series converges for all x. Don't forget about those two options. By the way, just as a little added thing, I kept saying that exponential growth dominates. We always have exponential growth around. x minus c raised to the nth power. In a power series, we're always going to have this pattern where I have at least one x minus c raised to the nth power. So I will always have exponential. The question is, do I have any other higher growths than exponential? Any faster growths than exponential? Exponential gets dominated by n factorial and n to the nth power. But if I have other types of growth, the exponential is always going to beat that one. So in a power series, we always have at least exponential growth because we always have at least x minus c raised to the nth power. And in all of these examples, that showed that. One observation that I would like to make, this is not a huge part of this section, but there's a couple of observations that I'll make. This power series is an infinite polynomial. We know how to take the derivatives of polynomial terms. When I take the derivative of a polynomial term, the shortcut rule says take the n out front and multiply by the coefficient, and then lower the exponent by 1. We can do that on infinitely many terms. N comes out front, multiplies by the coefficient, drop the exponent by 1. Notice that if you multiply by an n is just an n to the p type growth. Therefore, the fastest growth around in this expression, the dominant growth in the derivative expression terms, is going to have to be the same as the dominant growth in the function itself terms. So the terms of the power series and the terms of the derivative of the power series are going to be dominated by the same growth. And therefore, those two power series are going to have the same interval of convergence. However, because we're multiplying by n here, the endpoint convergence may be different. So in other words, a function and its derivative, when written out as a power series, have the same interval of convergence. They may be different at the endpoints. But other than the endpoints, they're going to have the same interval of convergence. They have the same endpoints, but we don't know if it converges or diverges at those endpoints. That's what we're saying. It turns out the same thing works when we integrate a function. If I have a power series, since each we're summing up, and I think of it as an infinite polynomial, we know how to integrate polynomial terms. We raise the exponent by 1 and then divide by that new exponent. And then we tack on a plus constant as well when we integrate. Again, n plus 1, that's an n to the p type growth. X to the n versus x to the n plus 1 are both exponential type growth. Therefore, if I find the interval of convergence for my function, that's going to be the same interval of convergence as the integral of the function, except when I plug in the endpoints here versus when I plug in the endpoints here, it might give me different convergence versus divergence options. So a function and its derivative are going to have the same interval of convergence. A function and its integral, or a function and its antiderivative, are going to have the same interval of convergence, except for how we converge at the endpoints. The endpoints will be the same, but just do we converge or diverge there? So the function, if the function is a power series, then it has the same interval of convergence as f prime and the antiderivative of f. Again, except maybe the endpoints could be different. Not different numbers, but convergence at the endpoints might be different. Let's take a look at this one. This is a fairly straightforward interval of convergence defined. Infinite sum of x to the nth power divided by n. That's my function. And then I'll find the interval of convergence for the derivative and the antiderivative using that same function. So we'll find the interval of convergence for the actual function and then the derivative and the antiderivative. All right. Exponential part is going to dominate. We have an exponential part and an end part. Now, in this case, the exponential part is just x to the n. And so I think of what happens here. The interval of convergence, very easy to find in this case because x serves as the r value. So it's from x of -1 to an x of +1. We're centered at 0, so the radius of convergence is 1. So exponential dominates, interval of convergence goes from -1 to 1, radius of convergence is 1. Now let's take and find what happens at the first endpoint. So in this case, if I plug in a -1, that's an alternating series and that converges. By the way, plugging in a -1 could also be written like this: f of -1 is equal to this. So that converges. And again, I'm just using the alternating series test. Okay. How about the other endpoint? What's going to happen when I plug in the value of +1? Well, when I plug in the value of +1, I get 1 to the n, which is just 1. We have seen this a bunch of times before. That's a p-series test with p of 1. So that's diverging. So the information about my original function is that the interval of convergence goes from -1 to 1. It converges at the lower endpoint, and it diverges at the higher endpoint. And that's it. I'm going to erase this part. Now let's take the derivative. if I take the derivative, I'm going to multiply by n out front of the x. So doing standard derivative techniques. The exponent comes down, n gets multiplied times x to the n minus 1, and then we're dividing by n here. Oh, you know what? I'm sorry. Let's pretend we start at n equals 1 because we don't want to start but with dividing by 0. Sorry. I just noticed that. So let's start with n equals 1. Now everything works out nicely. Hopefully that didn't bother anyone. So when I take the derivative, what's going to happen is this n and this n are going to cancel out, and I'm just going to be left with an infinite sum from 1 to infinity of x. Actually, let me rewrite this. Infinite sum of x to the n minus 1. So that is the derivative. Not sure why that changed, but it did. Notice that this is geometric. So it's going to have the same interval of convergence, the same radius of convergence. The only change is going to be what happens at the endpoints. What happens when x is -1 on this, and what happens when x is 1 at that on this series. If x is -1, I get this infinite series. Again, what I'm doing is I'm saying f prime of -1 is equal to this. This is an infinite series which diverges. And again, you could use the alternating series test to figure that out. The terms don't go to 0. So it's alternating, terms don't go to 0. If I plug in a positive 1 raised to any power is just 1. And so you're summing up 1 over and over and over, and that also diverges. That's the divergence rule there. So if I plug in, that is into the derivative, a -1, or I plug in a positive 1, they both diverge. And what I'm pointing out is the similarity to the function itself with the derivative. So the function itself, which I wrote as a power series, so the power series has the same interval of convergence, same radius of convergence, but at the endpoints, the original function converged at x equals -1, whereas my derivative now diverges at x equals -1. My original function diverged at x equals 1. My derivative also happened to diverge at x equals 1. Now we can also integrate this power series. Let's say we wanted to integrate this power series. Obviously, we're going to integrate it with respect to x. Then what I would do is I would raise the exponent by 1 and then multiply, excuse me, not multiply, divide by n plus 1. Once again, exponential is dominant. So once again, interval of convergence and radius of convergence are the same. That doesn't change. The endpoints may. Oh, I forgot. I should have added on a plus c to this to get any antiderivative, but adding on a constant doesn't change whether it converges or not. That plus c is like at the end. It's not plus c to each term. It's plus c to the after we've summed up everything. So after we've summed up everything, then add plus c. Some people, because of that potential for confusion, will write it up front as well. Constant plus that polynomial. Again, the plus c isn't going to matter as far as the convergence goes, but if I wanted to check the endpoints, I'd plug in a -1, and obviously I'd plug in a 1. When I plug in a 1, I just get a 1 in the numerator. Be careful on this denominator. This denominator I wrote as n plus 1 times n. You could have also written that as n squared plus n. So notice it's a quadratic in the denominator. It's degree 2, so therefore by a limit comparison to the p-series, it's going to converge when we have 1 on top. So it's a limit comparison to the p-series when p is 2. And then this, when I plug in -1, that's alternating. Terms are going to 0, so it converges. So in this case, instead of this series diverging, this series converged at x equals -1 and also converged at x equals +1. Again, the original function, we had 1 converge, 1 diverge. The derivative, both diverged, and then the antiderivative, both converged. So there we go. But the point is, all of these 3 series had the same interval and radius of convergence. Just what happened at the endpoints was a little bit different. That's the only difference. Just as a side note, that also happens here in example 2 as well. If you go through the properties, if you take an antiderivative or if you take the derivative The n factorial still dominates. So this is going to only converge at x equals 2, even after I take a derivative or I take an antiderivative. Same thing with this. This is going to converge from negative infinity to positive infinity. So this is going to converge for all x values. And if I take a derivative of this power series, it still converges at all x values. If I take the antiderivative of this power series, and that's any antiderivative, then it will also converge for all x values. So for all x values, this converges. Also the derivative, also the antiderivative or any antiderivative will converge for all x values. This one converged only at x equals 2. The derivative, the antiderivative will also converge only at x equals 2. So those are my convergence options. Obviously, kind of, in my opinion, the really weird cases, the toughest case is when we have an interval of convergence. But the nicest cases are when we converge for all x or only converge when x is the center. But this is the convergence for our series.